Welcome back. This is a problem set on Doppler effect. Doppler effect is when you hear a siren coming at you, say on a motorcycle or a police car, and as it comes to you, the sound seems to get higher. The pitch seems to get higher. When it goes away from you, the pitch seems to get lower. So if I were to have a source of a sound, and it's sending out wavelengths in all directions, like a sphere, getting further and further away from the source. And now that source itself is moving. What's going to happen is on the front side, it's going to seem to crowd those air waves that have already been made. And on the back side, it's going to make them go farther out. So any observer in the front is going to see these as being crowded and hear them as being closer together. The frequency is higher. Any observer on the back is going to have them be farther away, and its perceived frequency is going to be lower. So the formula is the perceived frequency. Okay, this is what you think you hear, whether it's high or low. So if two observers are listening to the same sound, one thinks it's high and the other thinks it's low, obviously the real sound is neither high or low, it's somewhere in the middle. So the perceived frequency of, say, the hearer in the front is equal to the actual frequency of the sound times the sum of the speed of the sound, okay, or the speed of sound, whatever sound travels in air, plus the speed of the velocity of the observer. See, the observer could be traveling. The observer doesn't have to be standing still. I can be in a car and hear a siren coming towards me, and I could be going away or forward, and I can still hear it rising in pitch, divided by the speed of sound minus the velocity of the source. So whoever came up with this formula, smart guy. This is amazing, because this would seem to me to be very complicated. Let's look at it's pretty straightforward though, so let's look at it. Dad is driving the family station wagon to Grandma's house when he gets tired and pulls over in a roadside rest to take a nap. Junior, who's sitting in the back seat, watches the trucks go by on the highway and notices that they make different sounds when they're coming towards him than when they do when they're going away. A. If a truck with a frequency of 850 hertz, so I guess that's the engine of the car, is traveling towards Junior with a speed of 27 meters per second, what frequency does Junior hear as the truck approaches? So Junior is not moving. Okay, so the velocity of the observer is 0. So we already know that f sub 0 is, so we have f sub 0 equals 85. Okay, the speed of sound, which is v, is 340. So this is hertz, sorry. 340 meters per second. That's how fast sound travels in space. And then the car is traveling away from him at 27 meters per second. So this would be the velocity of the source. So this is v sub s. All right, so we'll just put it together. So let's do the approach. So A says in approach, so you're going to have 85 times 340, okay, plus 0, because he's not moving, okay, so plus 0, divided by 340 minus 27. Okay, so it's 85 times 340 plus 0 divided by 340 minus 27. Okay, so calculation equals, and I get 92.3 hertz. Okay. All right, so what's the difference? Okay, as it's receding, what is the difference? Okay, he is going away at 27 miles, and now it says after the truck passes, what frequency does Junior hear as it moves away? Well, it's not going forward. See, if you look as it coming towards, you subtract the velocity of the source. This is a positive number. So you're subtracting 27 and you get 93 hertz. Okay? As it's going away, you should get a much lower number because it's sounding lower. So when you do it again, you're going to get 85 times 340 plus 0, because he's still stopped and sound still travels the same, divided by the speed of sound, 340, minus, and then you have a minus 27 because he's going away. Okay? That means that you're going to add the 27 and divide by a bigger number, and when you divide a fraction by a bigger number, the number gets smaller. So when you do the calculations here, it's going to be 78.7 hertz. Okay, so we have 92.3 hertz and 78.7 hertz. Very cool. Okay, let's look at another one. Okay, the next one says, the one way to tell a mosquito is about to sting is to listen for the Doppler shift as the mosquito is flying. In fact, that's why you can hear a mosquito, because you hear the rise and fall of its wings beating. The buzzing sound of a mosquito's wings is emitted at a frequency of 1050 hertz. Okay, so the mosquito hears 1050 hertz. If you hear a frequency of 1034 hertz, does this mean that the mosquito is coming in for a landing, or that it has just bit you and flying away? So what do you think? How would you tell? All right, is it higher than 1050 or lower? Okay, if it's lower, then the first answer means that he's flying away. So it means you've probably just been bitten. So he's flying away since you hear a lower pitch. Okay, and then the second one says, at what velocity is the mosquito flying? All right, so where is he flying away? So we want to know the velocity of how fast he's flying away. That means that we want to solve for the velocity of the source, the velocity of the mosquito. So we're having to solve for that. All right, so hope Mr. Spencer teaches you well. Let me kind of preview what we're going to do. This whole bottom, okay, this whole bottom has to now be moved to the top, okay? Then the F is in the way. The F is moved to the bottom. And then the speed of sound has to be brought to the other side, okay? Because remember, you're solving for V sub F, and V sub F is on the bottom inside a sum. So this is a pretty bad algebra problem, but I think you can do it. Let me just redo it for you. If you're going to solve, you'll have V sub F equals, okay, now V is, I said, bring it to the other side, so B is brought to the other side, and now that negative that's left with the V sub F have to be brought to the other side. Okay, so you'll have a negative, and then whatever was left. So you have the original frequency times the speed of sound times the velocity of the observer, okay, divided by the perceived frequency. Okay, ugly. So when we fill all this in, we're going to have the speed of sound is going to be 340 meters per second, and then we're going to subtract the original frequency, which is 1050 hertz. Multiply that. Okay, so now I need V, which is the speed of sound. That's 340 again. Okay, plus the observer, well, you're just standing still, I guess, so that's 0. And then we're going to divide by the perceived frequency, and we know that the perceived frequency is 1034. Okay, so you're going to multiply, divide, and then subtract from 340. And it means you're going to get a negative velocity because this is now smaller than 0, so your speed is going to be negative. All that means is it's moving away from you. It's not moving towards you, it's moving away. So it's moving at a velocity, but it's moving away from you, so it's perceived with a negative sign. And we have 5.26 meters per second. So you can actually trace how fast something's going by the shift in the sound. So if you knew what a frequency was of a motor, and you could tell how much that motor sound dipped, you could tell the speed of the fire truck or whatever it's passing you. pretty fast. This is awesome that you can figure out stuff simply by some kind of an observation. That's what science does.